So, what are main numerical features of a random variable? They are the expected value and the variance. An expected value, we usually use capital letter E to denote the expected value. In some textbooks, capital letter M is used. It is more common in Russian textbooks. So we have two separate definitions, two separate mathematical definitions of the expected value for discrete and continuous random variables. Actually, there is a common definition, but so you need to have some knowledge of functional analysis to be able to understand this common definition. So it will be more just easier for us just to use two separate definitions instead of providing you this additional knowledge from functional analysis. So for a discrete random variable, an expected value is defined as a sum, and each element of this sum is a product of a value of a random variable with its probability. So each value is multiplied by the probability of taking of this value, and we summarize, we add these multiplications, these products. And for a continuous random variable, an expected value is defined as an integral from minus infinity to plus infinity of x multiplied by the PDF. So you need to know the distribution to find the expected value of a random variable. So in discrete case, you need this table, or you need the BMF. In a continuous case, you need the PDF to find the expected value. So what is the physical meaning of the expected value? The physical meaning is the mean value. So actually, these terms are synonyms, and it is possible to change one with the other. So it is possible to say mean value instead of expected value, and vice versa. And sometimes when you are asked to find mean value, or when you are told in some problem that the mean value of something is equal to some number, so that means that they are talking about an expected value. So what is a mean value? I guess that just it can be understood just by your intuition. So that, let's imagine when you are told that the mean height of an adult man in Russia is 177 centimeters, for example. What does it mean? It means that all adult men have different heights, but if you measure, for example, heights of 1 million of adult men, and then you will calculate arithmetical mean, so you add these 1 million numbers and divide this sum by 1 million, you'll get something very close to this 177. So if you have many observations, big number of observations of this random variable, and you calculate an arithmetical mean of these observations, you get something very close to what we call an expected value. So the next feature is called variance. So for variance in English textbooks, the common notation is var, and also in Russian textbooks, sometimes they use capital letter D as a Russian term is. So the second important feature of a random variable is the variance. In English, the common notation for variance is var, 3 letters, VAR, and please be careful because there is another notation in statistics and in econometrics, value at risk, that is also shortened as VAR, but with capital V and capital R. So if you see capital V, small a, capital R, this is value at risk. This is not a variance. And if all 3 letters are small, or only the first V is capital, so this is the variance. So how the variance is defined? As you can see, this is expected value of x minus e of x squared. So seems a little bit sophisticated, but let's try to understand what is this. So x is the real value of actual value of the random variable. So the experiment is done, the random variable has already taken some value, and so x is this value, actual value that can be observed as the result of our experiment. So then e of x is the expected value of x, so e of x is the mean value. Then x minus e of x is the difference between actual value of the random variable and its mean value. In other words, we can say that this is deviation. So x minus e of x is a deviation of a random variable from its mean value. Then this deviation is squared, and then another expected value is taken of all these. So expected value is a mean value. So this is the mean square of a deviation of a random variable from its mean value. A little bit long, but it describes what is it. So one more time, mean square of a deviation of a random variable from its mean value. So this number, so variance, the value of variance, shows us how big the deviation can be. So if a variance of some random variable is small, is close to 0, that means that these random variables, that all its values are very close to its mean value. So deviations are very small. So all values this random variable takes are very close to its mean value. If variance is high, if variance is big, this means that so real actual values of this random variable can differ a lot from its mean value. For example, I told you that mean height of an adult man in our country is 177 centimeters. So if it is so, and if, let's say, 99% of all men would have their heights from 176 to 178 centimeters. So if 99% of all adult men would have their heights, difference of their heights from the mean height no more than 1 centimeter, this would mean that this random variable has very small variance. So its variance is very close to 0. And if, for example, there are adult men with their heights equal to 100 centimeters and to 300 centimeters, for example, and it is a common situation, and they then can be met very often. So this would mean that this random variable has big variance. So variance shows us how much a random variable can deviate from its mean value. Sometimes another value is used instead of variance, not the variance itself, but its square root of variance, and there is a special term for this value. It is called a standard deviation. So just it's almost the same. They both show how strong the difference between the actual value and the mean value of the random variable can be. Just in some cases, it's more convenient to use a standard deviation, and in some cases, it's more convenient to use the variance. So what are the main properties of the expected value and the variance? So here, A is a non-random number, and x and y are both random variables. So you can see that expected value of a non-random number is equal to this number itself. So y. And what is a non-random number? It's a number that does not depend on the outcome of the experiment. So every time the experiment is done, this number takes the same value. It is equal to itself every time. So that is why its mean value is equal to its own value. It simply doesn't change. Then, expected value of a sum of two random variables is equal to the sum of the expected values. And this is because the expected value is a sum in case of a discrete random variable and an integral in case of a continuous random variable. So that is why E of sum is equal to E of x plus E of y. Then E of ax is equal to A times E of x. So this is also because the expected value is either a sum or an integral. Then, if you need an expected value not of the capital X itself, not of the random variable x itself, but of some function of x, g of x. G is a function, can be any function. So this can be found using a formula very similar to the definition of the expected value, but this function x is taken of this function g is taken of xi in the discrete case and of x in continuous case. So probability in discrete case or the PDF in continuous case is multiplied not by the x itself, but by the g of x. So for example, if you need expected value of x squared, probability in discrete case or PDF in continuous case will be multiplied by x squared. So how about variance? Variance of a non-random number is 0. Why? Because you know that variance is a deviation. It shows a mean square of a deviation of a random variable from its mean value, but non-random number does not deviate anyhow. It is always equal to itself. It is always equal to its mean value. So that is why no deviation, no variance. Then variance of a times x is equal to a squared times variance of x, because variance is defined as expected value of a square, expected value of a squared deviation. Then variance of ax plus b is equal to a squared times variance of x. So you see that addition of a non-random number to a random variable does not affect the variance. Why it is so? So we can consider an example. So let's say that x is a salary of a random person, random employee of some firm. And so there is some difference in salaries in this firm. And let's say that the lowest salary is the salary of a cleaner, and it is equal to, let's say, 20,000 rubles. And the highest one is the salary of a director, and it is equal to, let's say, 200,000 rubles. And so the variance shows how these salaries differ from the mean salary. And the mean salary, let's say, is 15,000. So, and now let's imagine that all salaries are increased by 10,000 rubles. And so the salary of a cleaner is now not 20, but 30,000. Mean salary is now not 50, but 60,000. The salary of the CEO is not 200,000, but 210,000. So, did this affect the variance anyhow? It didn't. So, all the salaries increased by the same amount of money, by the same sum, and the mean salary also increased by 10,000, and so differences between all salaries and the mean one are the same after this. So this means that addition of a non-random number to a random variable does not affect the variance. And if all salaries are multiplied, for example, multiplied by 2, and the salary of a cleaner is not 20,000 but 40,000 now, and the salary of the CEO is not 200,000 but 400,000 now, so this will affect the variance, because range is now much wider, not from 20 to 200, but from 40 to 400. The range is wider, the variance is bigger. So, and the last one, the last property you should know is that variance of a sum is not always equal to the sum of variances. Actually, sometimes it is. So in some particular cases, there is an equality. In some particular cases, variance of x plus y is equal to variance of x plus variance of y. But in general, it is not so. And we will discuss this later. So what are these particular cases? Now, let's find the expected value, the variance, and the standard deviation of the random variable we already know. This is the distribution of the number of black balls when I choose 3 balls at random out of the box that initially contains 10 white and 2 black balls. And so this random variable can take 3 values, 0, 1, and 2, with probability 6 over 11, 9 over 22, and 1 over 22. So, as for the expected value, everything is very simple. So we know that expected value, according to a definition of a discrete random variable, is a sum of xi times p of xi. So it's just 0 times 6 over 11 plus 1 times 9 over 22 plus 2 times 1 over 22. So this is 0, this is 9 over 22, and this is 2 over 22. So 9 plus 2 is 11, and I have 11 over 22, and 11 is cancelled, and this is 1/2. So expected value is 1/2. You should understand that expected value can be equal to something that is not a possible value of your random variable. So we see that the random variable can take values 0 or 1 or 2, but expected value is 1/2. So we don't see 1/2 here, but it is a normal situation. So for example, you can hear something like average birth rate in a given country is 1.8 children per woman. So you know that each woman can give birth only to an integer number of children, but what does it mean, 1.8? That means that if we add all children born and divide by the number of their mothers, we'll get this number. So it is possible for an average value, for an expected value, to be something that is not among the values that the random variable can take. So e of x squared is 0 squared times 6 over 11 plus 1 squared times 9 over 22 plus 2 squared times 1 over 22. So this is 0 plus 9 over 22 plus 4 over 22. 9 plus 4 is 13. So 13 over 22. This is e of x squared. And variance is e of x squared minus squared e of x. So variance is equal to 13 over 22 minus 1 over 2 squared, 13 over 22 minus 1 over 4. So this is 15 over 44, or approximately in decimal numbers, 0.34. Or we can say 341. So this is the variance, and if we want to find also standard deviation, the sigma is the square root of the variance So square root of 0.341, that is approximately 0.584. So that is how we can find expected value, variance, and standard deviation for a discrete random variable with known distribution. So if the PMF or the distribution table is given, everything is just very simple. Another example. Let's say that 2 dice are rolled, and let x be minimal of 2 numbers we get after 2 dice are rolled, and y be maximum of these 2 numbers. So two dice are rolled, and x is a minimum of the 2 numbers, and y is the maximum of these 2 numbers. And so we want to know the distributions of x and y and their expected values. So how this can be done? We should describe the sample space as the first step. So we are to understand what is the experiment and how many outcomes it has. So to describe a sample space. So 2 dice, the first dice can give us 1 or 2 or 3 or 4 or 5 or 6. The same is for the second one. 1 or 2 or 3 or 4 or 5 or 6. So our sample space has 6 times 6, 36 elements. So our experiment has 36 possible outcomes. And now let's try to fill the distribution tables for x and for y. So x is a minimal of 2 numbers we get, and what values x can take? Obviously 1 or 2 or 3 or 4 or 5 or 6. So x can take any of these 6 numbers, and y also. So let's start with x, with the x. So for x, I have a table. One, 2, 3, 4, 5, 6. So x is a minimum of 2 numbers. What are the outcomes favorable for the situation when x is equal to 1? Which of these 36 outcomes are favorable for this event? Are favorable for the situation when the minimum of 2 numbers we get is equal to 1. So if we get 1, 1, then minimum is 1. If we get 1, 2, the minimum is 1. 1, 3, 1, 4, 1, 5, 1, 6, all these situations give us 1 as a minimum of these 2 numbers. Then 2, 1, also minimum is 1. 3, 1, 4, 1, 5, 1, 6, 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 outcomes are 11 out of 36 are favorable for this event. So its probability is 11 over 36. Then, when minimum is equal to 2. So when, for example, I have pair 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 2, 4, 2, 5, 2, 6, 2. So these are outcomes such that minimum is equal to 2. The number of such outcomes is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So 9 over 36. Then outcomes favorable for these situations are these ones. And their number is, if we count, is 7. So here I have 7 over 36. Then, when minimum is equal to 4, when I have 4, 4, 4, 5, 4, 6, 5, 4, 6, 4. So there are 5 outcomes favorable for this event. Minimum is 5 in these 3 cases. So 3 over 36, and so this is the only outcome favorable for this situation. So minimum is equal to 6 only, and if we have 6 on both dice, so 1 over 36. So this is the distribution of x, and now after we have the distribution, we can find the expected value. So expected value of x is 1 times 11 over 36 plus 2 times 9 over 36 plus 3 times 7 over 36 plus 4 times 5 over 36 plus 5 times 3 over 36 plus 6 times 1 over 36. So this is 1 over 36, and here I have 11 plus 18 plus 21 plus 20 plus 15 plus 6. So this is 91 over 36, or approximately 2.528. So now we can do the same with y. So for y, the first step is to fill the table. So y can also be either 1 or 2 or 3 or 4 or 5 or 6. And now we are to find distribution. So y is a maximum of these of 2 numbers we get. So situation when y is equal to 1 happens only if we get 1, 1, only if this pair. So here we have 1 over 36. Then maximum is equal to 2 when we have 2, 1, 2, 2, and 1, 2. These 3 outcomes. So probably you have already guessed what we will have next. So here we have 11, 9, 7, 5, 3, 1. And here vice versa, 1, 3, 5, 7, 9, 11. So here we have 5 over 36, 7 over 36, 9 over 36, and 11 over 36. And now let's find the expected value. Expected value of y is 1 times 1 over 36 plus 2 times 3 over 36 plus 3 times 5 over 36 plus 4 times 7 over 36 plus 5 times 9 over 36 plus 6 times 11 over 36. So this is 1 over 36, and here 1 plus 6 plus 15 plus 28 plus 45 plus 66. And this is equal to 161 over 36, or in decimal numbers approximately 4.472. So this is average minimal number, and this is average maximal number when the dice is rolled twice.